For a group of buildings with a total single-phase load of 35 to 50 kV amps, a 3-phase 200 amp panel board is suitable. Run 4 secondary wires consisting of phases A, B, and C along with the neutral conductor from the meter to the main building. Connect the secondary wires to the panel board in the following manner. Phase A to bus 1 also denoted as A, phase B to bus 2 also denoted as B. Phase C to bus 3 also denoted as C. Connect the neutral conductor to the neutral bus bar. It is important to balance the single-phase loads across the 3 phases A, B, and C. Aim for approximately 1/3 of the total load on each phase. This will help minimize current imbalance and ensure efficient operation of the transformer. For the underground wiring to the 5 homes, use direct buried THWN or XHHW aluminum conductors. Size the conductors based on the calculated load and the distance of the run to each home. A weatherproof, non-metallic trough should be used to house the secondary conductors and split bolt connectors. Install 5 fuse disconnect switches, each rated for 100 amps. Each disconnect switch will protect a home's 100 amp panel. Run separate conductors from the disconnect switches to each home's 100 amp panel. The meter must be rated for the full calculated load of the system. Establish a proper grounding system according to National Electrical Code, NEC requirements. Perform insulation resistance and continuity testing on all conductors and equipment prior to energizing the system. Have a qualified electrical inspector approve the entire installation to ensure compliance with local codes and safety standards. Considerations for conductor sizing need to be addressed. Conductor sizing must adhere to the NEC, specifically Article 310. The ampacity of the conductors must be sufficient to carry the calculated load, considering any applicable derating factors for ambient temperature, the number of conductors in a raceway or cable, and voltage drop. Aluminum conductors are often used for the service entrance due to their cost effectiveness, but their ampacity must be carefully considered and properly sized. Proper termination is crucial. Ensure that all conductors are properly terminated using appropriate connectors and lugs. Torque connections to the manufacturer's specifications to prevent loose connections, which can lead to overheating and potential failures. Use antioxidant compounds on aluminum connections to prevent corrosion. For underground installations, ensure that the conductors are buried at the proper depth as required by the NEC and local codes. This protects the conductors from physical damage. Mark the location of the underground conductors with warning tape to prevent accidental digging in the future. Grounding is a critical safety aspect that must be addressed meticulously. The grounding system must comply with NEC Article 250. Firstly, a grounding electrode system must be established, typically consisting of a ground rod, ground ring, or connection to the metal water pipe. Secondly, the neutral conductor must be bonded to the grounding electrode system at the service entrance. Thirdly, equipment grounding conductors must be installed with all branch circuits to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. Surge protection should be considered. Installing surge protective devices, SPDs, at the main panel and subpanels can help protect sensitive electronic equipment from voltage surges caused by lightning or utility switching. SPD divert excess voltage to ground, preventing damage to connected equipment. Overcurrent protection should be carefully considered. Each circuit must be protected by an appropriate overcurrent protective device, such as a circuit breaker or fuse. The rating of the overcurrent device must be matched to the ampacity of the conductors it protects. Coordination of overcurrent devices is important to ensure that a fault on one branch circuit does not cause a larger portion of the system to shut down. Labeling is important too. Clearly label all panels, circuits, and disconnect switches. This helps with troubleshooting and maintenance. Panel schedule should be up to date and accurate. Warning labels should be placed at appropriate locations to alert personnel to potential hazards. Safety is paramount. Always to energize circuits before working on them. Use appropriate personal protective equipment, PPE, such as gloves, safety glasses, and insulated tools. Follow lockout-tagout procedures to prevent accidental energization of circuits during maintenance or repair. Coordination with the utility company is required. Coordinate with the local utility company, Rio Power Co., regarding the service connection, metering requirements, and any specific requirements they may have. Ensure that the installation complies with all utility regulations and standards. Future expansion can be considered. When designing the electrical system, consider the possibility of future expansion or increased load. Oversize the service entrance conductors and panel board capacity to accommodate future needs. Install spare conduits to facilitate the addition of new circuits. Documentation is also important. Maintain accurate documentation of the electrical system, including panel schedules, wiring diagrams, and equipment specifications. This documentation is essential for troubleshooting, maintenance, and future modifications. Training is required. Ensure that all personnel who will be working on or maintaining the electrical system are properly trained and qualified. Training should include safety procedures, troubleshooting techniques, and knowledge of the NEC. Regular inspections and maintenance are essential for ensuring the continued safe and reliable operation of the electrical system. Schedule periodic inspections to identify and correct any potential problems. Perform preventative maintenance on equipment such as circuit breakers and disconnect switches. The neutral conductor carries the unbalanced current between the phases in a three-phase system. It is crucial to ensure that the neutral conductor is properly sized and connected to prevent voltage imbalances and potential hazards. The NEC specifies requirements for neutral conductor sizing in Article 220.61. Voltage drop is a concern when running conductors over long distances. Excessive voltage drop can cause equipment to malfunction and reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Calculate the voltage drop using the appropriate formulas and adjust the conductor size as needed to stay within the recommended limits. Short circuit current rating, SCCR, is an important consideration for all electrical equipment. The SCCR of a panel board or disconnect switch must be equal to or greater than the available fault current at its location. This ensures that the equipment can safely withstand a short circuit event without failing or causing a fire. Determine the available fault current through a short circuit study and select equipment with an appropriate SCCR. Arc flash hazard analysis should be performed to determine the potential arc flash hazards at various points in the electrical system. This analysis involves calculating the incident energy and determining the appropriate personal protective equipment (PPE) required for working on energized equipment. Label equipment with arc flash warning labels to alert personnel to potential hazards. Harmonics are non-sinusoidal currents or voltages that can distort the electrical waveform and cause problems such as overheating of transformers and conductors, malfunctioning of sensitive electronic equipment, and increased energy losses. Harmonic filters can be installed to mitigate the effects of harmonics if they are a significant problem. Power quality monitoring can be used to assess the quality of the electrical power and identify any power quality problems such as voltage sags, swells, or harmonics. Power quality meters can be installed to continuously monitor voltage, current, frequency, and other parameters. Energy efficiency can be improved by using energy-efficient lighting, motors, and other equipment. Install occupancy sensors to turn off lights in unoccupied areas. Use variable frequency drives, VFDs, to control the speed of motors and reduce energy consumption. Consider using renewable energy sources such as solar panels to generate electricity and reduce reliance on the grid. Building codes and standards are important to follow. Ensure that the electrical installation complies with all applicable building codes and standards, including the NEC, the International Building Code, (IC), and any local codes or ordinances. Obtain the necessary permits and inspections to ensure compliance. The NEC Article 110 covers the general requirements for electrical installations, including workmanship, equipment approval, and access to electrical equipment. Follow these requirements to ensure a safe and reliable installation. Proper planning and design are essential for a successful electrical installation. Take the time to carefully plan the system, considering all applicable codes, standards, and regulations. Consult with a qualified electrical engineer or contractor to ensure that the system is properly designed and installed. The transformer is the heart of the electrical distribution system. It steps down the voltage from the utility's high-voltage distribution system to a lower voltage suitable for use in buildings and homes. The transformer must be properly sized to handle the load and must be protected by overcurrent devices. The transformer's impedance affects the available fault current at the secondary terminals. A lower impedance transformer will result in a higher available fault current. A transformer's voltage regulation is the change in secondary voltage from no load to full load. A transformer with good voltage regulation will maintain a relatively constant voltage under varying load conditions. The transformer's efficiency is the ratio of output power to input power. A more efficient transformer will consume less energy and save money on electricity bills. Consider using a dry-type transformer for indoor installations. Dry-type transformers are air-cooled and do not require the use of oil or other liquids, reducing the risk of leaks and spills. Pad-mounted transformers are typically used for outdoor installations. Pad-mounted transformers are enclosed in a tamper-resistant enclosure and are mounted on a concrete pad. The transformer's kVA rating must be sufficient to handle the total load connected to it. Calculate the total load by adding up the kVA of all the connected equipment and appliances. The transformer's primary voltage must match the utility's distribution voltage. The transformer's secondary voltage must match the voltage required by the connected equipment and appliances. A 208Y/120 volts transformer provides three-phase power at 208 volts and single-phase power at 120 volts. This is a common voltage for commercial and industrial applications. The Y configuration provides a neutral point that is grounded, providing a stable reference for the single-phase voltages. Delta-connected transformers do not have a neutral point and are typically used for applications where only three-phase power is required. Open delta transformers are used to provide three-phase power when only two transformers are available. Open delta transformers have a reduced capacity compared to a full three-transformer bank. Auto transformers are used to step up or step down voltage by a small amount. Auto transformers are more efficient than traditional transformers but do not provide electrical isolation between the primary and secondary windings. Isolation transformers are used to provide electrical isolation between the primary and secondary windings. Isolation transformers are used to protect sensitive electronic equipment from voltage spikes and surges. Control transformers are used to provide power to control circuits. Control transformers typically have a low kVA rating and are designed to provide a stable voltage to control devices such as relays and contactors. Instrument transformers are used to measure voltage and current. Instrument transformers provide a scaled-down version of the voltage or current that can be safely measured by metering equipment. Current transformers (CTs) are used to measure current. CT are connected in series with the conductor being measured and provide a current output that is proportional to the current flowing through the conductor. Potential transformers (PTs) are used to measure voltage. PT are connected in parallel with the circuit being measured and provide a voltage output that is proportional to the voltage of the circuit. The National Electrical Code (NEC) is a set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC is updated every 3 years and is adopted by most states and local jurisdictions. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a law itself, but it is often adopted into law by state and local governments. Compliance with the NEC is essential for ensuring the safety of electrical installations. The NEC is published by the National Fire Protection Association (NFPA). The NFPA is a non-profit organization that develops and publishes codes and standards related to fire safety. The NEC is a consensus standard, meaning that it is developed by a committee of experts representing a variety of interests. The NEC is based on sound engineering principles and is designed to protect people and property from electrical hazards. The NEC is a valuable resource for electricians, engineers, and other professionals involved in the electrical industry. Understanding the NEC is essential for designing and installing safe and reliable electrical systems. The NEC is available for purchase from the NFPA and other sources. The NEC can also be accessed online through subscription services. The NEC is a complex document, but it is well organized and easy to navigate. The NEC is divided into chapters, articles, and sections. Each section contains specific requirements for electrical installations. The NEC includes tables and figures that provide additional information and guidance. The NEC is constantly evolving to keep pace with new technologies and changing safety concerns. Staying up to date with the latest version of the NEC is essential for ensuring compliance and safety. The NEC is an indispensable tool for anyone involved in the electrical industry. By following the requirements of the NEC, you can help ensure the safety of people and property from electrical hazards.